Okay, so in this video, we're going to look at the definition of the limit of an infinite sequence. So by an infinite sequence, I just mean a sequence of numbers, which we'll denote as an, which we write as a1, a2, a3, a4, a5, etc. So for example, this sequence could look like this. It could be an is equal to n squared, and then we'd have a sequence which looked like 1, 4, 9, 16, and so on. Or we could have a sequence which looks like this, an is equal to 1 over n, and then it would look like 1, 1/2, 1/3, 1/4, and so on. So this is all we mean by an infinite sequence. And now we want to ask the following question. We want to ask, what does an look like when n gets really big? Or in other words, what is the limit of an as n tends to infinity? So what we're really thinking of here is, what does an look like when n goes to infinity? So we need to formulate a definition of the limit. So we say that the limit as n tends to infinity of a sequence an is equal to a number L if for all epsilon greater than 0, so for any number you pick greater than 0, there exists some capital N in the natural numbers, so 1, 2, 3, 4, etc., such that for all small n greater than or equal to capital N, we have that an minus L is less than epsilon. So this is the definition of a sequence converging to a limit L. So what does this definition really mean? It means that no matter which number you choose, epsilon, there's always a natural number n, such that if we choose points above this point n in a sequence, an is going to get really close to the number L. So no matter how small you pick epsilon, there becomes a point such that every point after this point is within epsilon of the number L. So we can try and draw this on a graph to get a better idea of what is going on. Okay, so say we take some graph with n on the x-axis and an on the y-axis, and we just choose any sequence for an. So say an looks something like this. This is a1, this is a2, a3 is maybe here, a4, a5, and so on. And we want to try and see what the limit is of an as n tends to infinity. Obviously here we've only drawn finitely many points, but we can try and get an idea of what is going on just with this drawing. So say we think an converges to L, which is around here, then what we need to do is pick any epsilon greater than 0 and draw a strip around L of size epsilon. So say we pick epsilon to be quite big, so epsilon is like this big. Then we draw a strip around L of size epsilon. So this is our strip around L of size epsilon, this strip here. And what we want is to find some capital N such that for all small n greater than or equal to capital N, an is in this strip. So here we see that the only points outside this strip are a1 and a2. So if we continue, we have a3 is here. So if we pick a capital N to be 3, then every an after this point, a3, is in this strip. But say we choose epsilon to be far smaller, so say this is our strip of size epsilon. We want to repeat the same process. We want to find a capital N such that for all an after this point, a capital N, the points will be in this strip of size epsilon. So here we have a1 is not inside, a2 is not inside, a3 is, but a4 isn't, a5 isn't, a6 is, a7 isn't, and then after this point, this would be a8. We see that every point is in this strip. So we can choose n, capital N, to be 8, and then every point after this point is in the strip. So we'll have that an is within epsilon of the point L. And the point is, we need to be able to do this for every epsilon we choose. So no matter how small you choose epsilon, we're going to find a point n, capital N, such that the sequence fits in this strip of size epsilon after this point, capital N. Now obviously it's hard to draw this for any epsilon because you need to choose epsilon to be really small, but this is the idea. So in the next videos, we'll look at some examples of how this definition works in practice and of how to find limits.